Hello, everybody. Great to see a packed room here. Today, in this evening, we're in the Big Things meetup about stream processing. We'll be presenting today Amit Sela from PayPal and Tyler from Google. They will be talking mostly about Apache Beam and the implementation of stream processing over the tools that we know today as Flink and Spark. And I'll let you start speaking.
Hi, so good evening everyone, thank you for coming. My name is Amit from PayPal, and today I'm going to talk about what my team and I have learned for the past year while developing a stream processing platform for PayPal. In the next 45 minutes or so, I hope to share with you some of our experience, the challenges we've met, and maybe some solutions that we found. So, a little bit about me. I'm a software engineer working at PayPal, working on big data platforms. I'm also an open source enthusiast. I've been working with open source for the past 5 years. Worked with Hadoop, Yarn, MapReduce, HDFS. I've spent nearly 2 years working on HBase. Recently working with Kafka and Spark, and started working with a Google SDK called Dataflow, which turned into Apache Beam. I'm a committer for Apache Beam, and I currently lead the development efforts for the Spark runner. So basically, our agenda today will talk about the following. We'll start with why stream processing. I guess we all need a reason to do something, or some of us need. And we'll check why stream processing, why do we need it, what are the benefits. We'll also talk about how to choose the right framework for you. I will share our experience with how we chose the right framework for us, and hopefully this will provide you with some insights. Next, we'll visit the challenges that we found when working on stream processing. We'll visit some solutions and also see some gaps that we still have. And this whole journey will lead us to some thoughts of a model. This is not a well-thought model. Nothing of an academic paper or something like that. It's just a sort of perception that's coming from the hardships that we've had and lessons that we've learned. And finally, I'll go over the future of Spark, which these days is it has version 2 in pre-release, I think, and Spark Summit is currently happening. Yeah, so it's currently happening. The preview version is out, so that's going to be interesting for anyone using Spark or want to use Spark streaming. So, I guess why do we need stream processing? Basically, I guess your bosses are going to need some motivation to let you do whatever you want with those frameworks. So, the first thing I would say is that this is how your data behaves. I mean, you have a user that uses a mobile app, and he's currently buying something, right? So he made a transaction, and one of your servers is logging this transaction. And this log transaction is becoming a piece of data, and it's flowing through the pipelines, through your system. And this is how things behave. This is how data behaves. It reacts, like action equals reaction, right? It reacts to whatever your software does, which is influenced by what your user does. So I would argue that why use your data differently when it behaves this way? And let's visit some examples. I mean, with ETL, it's nothing new, right? We know ETL, we've been doing that for quite a while with batch. We had daily ETLs, and then we had hourly ETLs, and I even know of some cases where they have 15 minutes ETLs. And they do transformations and filtering and sometimes enrichment with static data. And that's great, but why wait? You could do the same. This is fairly simple. It's mostly stateless computations. And you can do the same with reduced I/O. You don't have to write your data to HDFS into the directory and then read it off there and rewrite it after it's been all cleaned up and prepared to whatever analytical computations you have planned in mind. So regarding the analytical computations, you want to do real-time analytics. Why do you want to do real-time analytics? I mean, you normally do top-end computations to figure out trends. You do counts and aggregations and sliding windows. And you get this nice dashboards. And then once every 15 minutes, they just pop and get updated. But this is not a real mirroring of how your data behaves, because your data constantly changes. And the mirror, or the mirroring of how your business behaves with those dashboards is not really showing as it should. So doing real-time analytics will actually provide you with real insights on time. And one way you could use those real-time analytics is with monitoring. And I'm not talking about monitoring processes or network or I/O. I'm talking about, say you have, you're an ad company, and you have an algorithm that manages your ad campaign, and for some reason capping stopped working, and now your users are being bombarded with the same message, with the same ad over and over again. So you probably want to know about it as soon as possible. And if your data flows in and you process it as these things happen, you could notice this. Real-time fraud analysis is more close to heart. So basically what you could do is keep data points updated on the entities that you want to check if they are fraudulent or not. And this way you can update their status in near real time, and not just find out like the next day or something that this entity is maybe fraudulent. And also real-time classification. So for real-time classification, well, we also use it in fraud, but this is also a part of recommender systems, which is quite popular for many companies, also in Israel. And I think historically or usually, real-time classification is done in batch. You basically like take a week-old or month-old data, you run your pet job, you train the model, and then you use it. But by the time you run the next job after it, some time passes by, and you could actually keep your classifier up to date using stream processing until the next batch arrives. This is not Lambda architecture or something, but just a way to maybe get the benefit from batch and streaming together. So finally you're gonna end up with new abilities and new tools. It's the same data, it's the same computation, the same analytics, but it's faster. It's more, it represents your business better. And so you might get used to it. Just don't act like this guy, where Louis C.K. is speaking on Internet on Planes. So our journey begins with choosing technology. This is basically, I think, how, at least up until now, you didn't have a choice, and you had to do it like this. When you build a platform that revolves around a core technology, you have to choose the technology. And we knew that we were going with open source software all along. I think that the Hadoop ecosystem proved that open source solutions are good. They actually move huge billion-dollar industries now, and we decided to go with open source. So I will not be relating to any out-of-the-box products that are out there. And we've also decided to only go with Apache top-level projects, which are what Apache calls mature projects. So, for example, we did take a look at Apache Flink, and it seemed very nice at the time, but it was not a top-level project, so it did not make the cut. So we ended up with Apache Storm, Apache Samza, and Spark, and that's when the fun began. I mean, we did POCs and we did paper analysis, and we even remembered to check what our analytical needs are for real. And then, well, I'm going to go over the paper analysis and do a comparison between those frameworks. So this is sort of a summation of what we ended up with after our paper analysis. And I'm going to start with guarantees. Basically, guarantees, processing guarantees, fault tolerance guarantees are the guarantees that your framework declares or states that it supports. Now, you have at most once, it's not here because there was never an option for us. This means data loss. You have at least once, which means that some of the data is going to be reprocessed. And you have exactly once, which means that all the data is going to be processed exactly once. Well, not exactly once. It's all suffixed by the word semantics usually, because it never actually being processed just once. But it provides the same behavior. So we took a look at the documentation, we saw that, and we said, yay. We have exactly one semantics with Spark, everyone wants this, we got it, nice. Let's move on. So then we moved on to stateful processing. And I talked about ETL, but ETL is just one use case, and we have far more interesting analytical questions to process. So with stateful processing, we sort of lost Storm, because Storm tells you to sort of roll it up your own. Just do something on your own, and there are some examples on the internet, and good luck. And you could use Trident, but Storm was actually a candidate on its own, because Trident gets Storm to behave like Spark and lose its relative edge in other places. So I think this is where Storm kind of got behind in the race. And we actually found that Samza has a really interesting solution. They have an architecture that says that each Samza processor has its own local database, which is a sort of a logical partition in a logical distributed database. This was LevelDB, it's RocksDB now, I think. It uses Kafka replication for fault tolerance, and it's very nice, actually. But it also seemed a bit cumbersome, because this whole thing also runs on Yarn. And it seemed like a lot of moving parts, and we need to monitor this DB, for example. How do we know if something failed? We just fail on the stream. And so, too many moving parts for us, and we took a look at dedicated D stream from Spark. Now, it wasn't love at first sight with dedicated D stream, not for stateful processing, and we're gonna see it later. But we had faith in the Spark community to make it better. And it wasn't because we are great believers, but because we actually took a look at the community. And this was an important part of how we evaluate open source software, the community. We saw great adoption and support. We took a look at the GitHub repos and what's going on there, the trends and number of contributors. And Spark is also, it's been managed as a product as well for Databricks. So we had a great adoption. It's supported by a company which tries to make money of it. And this was a really great benefit for us concerning the community. And finally, Spark provided a straightforward API for analytics. It had machine learning libraries which were very popular, still are, I think. Spark SQL, and it had native support for batch, which is also going to be eventually a part of our platform. So we said that that's a good win, and I think that probably this is where we knew that Spark is going to be the winner. But I failed to mention streaming model and performance. And the reason is that, well, Spark's streaming model is micro-batching, and for some of you who don't know, what this basically means is that the receiving nodes are sort of waiting for a set interval, say a second, to like batch up a bunch of data, and then they ship it, and it kind of behaves like Spark batch jobs, but they keep going one after the other. And I could argue that this doesn't really matter, because if you have your pipeline modeled correctly, this becomes a latency issue. And in the performance tab, you can see that it's medium latency, which means second plus, and we were fine with that. If your use case is something else, it probably won't be as good for you. I think that for ETL use cases, Storm would probably be a great solution. And about Samza, well, I don't know. I'm undecided about it. So.
Isn't that configurable, the amount of data that you're going to stream out?
Yeah, but it's configurable by time. It's like they open a timer, they say, okay, whatever got in, and we're batching it. So if you have something like reading from Kafka, this could be a lot of events. And if you're just listening on some socket, I don't know, then depends. Great. So this is like a preview to some of the challenges we're going to visit. And the first challenge we saw was that streaming tends to misbehave. Streaming does not come in order. You have out-of-order data, you have late data. This could be because of network issues. This could be because your front-end server is restarting and sending all the logs. It didn't send yet. It could be because the user who used your app on the phone is now reconnecting to the network and uploading data. And this is very confusing because Spark provided streaming Windows APIs, right? I don't know how many of you know, they have like this magic dot window and you're done. But those are processing time windows. And what this means is that this also batches up the data, and it means that it only takes, like, it relates to the data that flows in the pipeline. It does not look at the event time, which is the real time of the data. And this was very confusing for us. So in order to handle this, we knew we had to go to stateful processing, because that's the only thing you have left with stream. And with stateful processing, the interesting parts we took a look at were event time windows and a little bit about sessions, but I'm not going to talk about that. And the third thing is fault tolerance. I was very happy with exactly one semantics in the documentation, and then I found out that you have to integrate your pipeline with something. I mean, you do want to read your data off somewhere, and you want to write it to somewhere. And those integrations are weaknesses for the pipeline, because it doesn't matter which framework you use. If it doesn't have a very good tight integration with the sources, the sink you use, you're probably going to break there and go down the scale of your fault tolerance guarantees. So it's like the weakest link, I guess. So the challenges with stateful processing in Spark. So up there you see update state by key. This was Spark's original API for stateful processing, and this was very problematic in two ways. First of all, it behaves like a map-like RDD of key state pairs, and what it means is that you have a collection in memory of key set pairs, and for every key that you're processing, you actually scan the entire collection in order to update it. And this is very inefficient. And the second thing is the fact that the dedicated dstream is being checkpointed for failures. And this means that as your key set cardinality grows, your data grows, and the dstream becomes heavier, and checkpointing becomes heavier, and it sort of behaves like a burden to the stream. So with 1.6, they've introduced map with state, and that was actually a great improvement in terms of seeking the update, because that's a map. Okay, inside it's some sort of a distributed hash map or something. No. An RDD is not mapped. They have behind there some weak hash map, something, I don't remember. I did visit the code once. But still, the issue with things being in memory, spilled to disk, in checkpoints, and the fact that your dstream is becoming more and more, it's becoming heavier as your state is becoming larger. Unless you clear your state, and they did add TTLs for that as well. So in this case, we've decided that this is not robust enough for us, and thanks to Scala, we've implemented implicit, and it was like a great win for me personally to write an implicit something. And And we actually just changed the internals and used the update function when we did a read update write from Aerospike. We ended up with 0 to 3 millisecond in 95th percentile, and for us that was great. And another motivation for that was having the state externally. We did want to be able to take a look at the state. The state inside the stream is hidden. You can't look at it unless you do. You open like another branch in the graph that spills the state. So we wanted to take a look at it in a decoupled way. Wanted to be able to maybe historically look at it, stuff like that. And it doesn't burden the stream anymore. So that was a great solution for us. And I would even say that it was a brilliant solution, but that would be a lie because we actually didn't know how good of a solution this is going to be. But you'll wait and see. About fault tolerance. So I've mentioned exactly one semantics, and especially the semantics, and the fact that the way things work is that they actually reprocess, but they don't commit the process. So it's exactly once. So this is like a pseudocode in Scala for a task. A task is the smallest job that Spark does. It's a single-threaded execution of your transformation or the lambda that you apply. And it's applied to a partition of elements. So say I have 3 elements. They are keyed and they have state and the value that updates the state. And say that element number 1 succeeded, also element number 2, and with element number 3, the node crashed, and everything restarts on another node. So what happens is that this did not create the next RDD in the lineage. So that's fine, no harm, right? But what if this transformation was actually writing to a database? So you would be overcounting, right? And what if you're reading off, say, Kafka? You have to know where you left off. I mean, you could reread, right? But you have to know that as well. You can't just say, I'm reading this offset until this offset and that's it. So this is how our basic pipeline looks most of the time. We read off Kafka, we write to Kafka, and sometimes we also write to a KV store. And with Spark 1.3, I think they introduced write-ahead logs to handle the 0 data loss. And with 1.4, it was getting better, and Kafka got a special treatment, and they've used direct Kafka, direct streams. And what it actually does is that it aligns the Spark partition with the Kafka partition, so each partition is aware of the offsets it came from in Kafka. And in case of reprocessing, it just starts from the offset. And this is great. It provides 0 data loss, but we still didn't get exactly one semantics on the other side, on writing. And there are some nice tricks to do that. They are per use case. For example, if you don't have any modification to the partitions, you can use this partition offset as your version in the database. And then if you have reprocessing, you will not reapply the transaction for the same partition. But what happens if you do what we do, and you also use the state? So the state will probably get dirty. It will overcount. And those are really hard challenges. I don't know any system today that provides this for all integrations, and usually it's work to do that for each integration. But for our use case, at least once was okay in some cases. At least once and idempotency are exactly once. That's like the best equation you could hope for with at least once. But also for statistics, in most times, at least once is okay. If you have a well-monitored platform and you're aware of how many failures you have in 5 minutes, hour, and so on, you can live with it, because eventually statistics will survive these small changes or inaccuracies. So this is how we dealt with the current situation in Spark. So to summarize the challenges, I think that stateful processing is something that we did not grasp right away. like how important it is and handling out of order and late data. And I think that our choice of external KV store is going to prove itself, and you're going to see that. And this was like a homemade solution for us. With the situation with dirty state, well, we monitor this. This provides statistics, so eventually that's fine as long as it doesn't happen too much. But we're also working on this, and we could use versions in some way. And for fault tolerance guarantees or end-to-end guarantees, the community provided zero data loss and at least one semantics. And in some use cases, some very creative solutions for exactly once.
I've got to ask a question about the size, the volume and everything. How big is your data? Because when you're keeping state on your processing or on your stream processing, that depends on how much you need to persist to a different external KV store or whatever.
Yeah.
So it really matters, I think.
Yeah.
I think
So
most people want
I'm not going to relate to volumes or rates or stuff like that, because then I would have to wait like a lot of time for legal to contact me. And yeah. So, but I will relate to what you're asking in a way that it's a trade-off, right? You're going out, you're doing out calls to update the state, and it takes time. It's usually less than 1 millisecond, but it's time. If you have
Per
a
event,
million,
probably.
yeah, it's per event, but it's parallelized as well. I mean, you have, I don't know, 20 executors, and you have 8 tasks per executor, so we have 160 connections open at the same time, and it goes the same for the D stream, for the dedicated D stream. If it's not parallelized enough, it's too heavy. Even if it might fit in memory, like just fit in memory, you will wait a long time for this reading and writing of checkpoints.
Yeah, it depends on the size of the cluster as well.
Yeah.
The Spark cluster, because you need many resources for that.
Exactly. So you need a lot of resources, and yeah. And also, if you have a lot of resources on the state store that you use as well, yeah, that's important. Anyone? Yes.
Can you go back to the slide with the key value? So can't you just store already seen keys into the external key value store?
Can't I just what? Sorry?
You said you have a problem with exactly once processing, that it enables to do exactly once processing,
Yeah.
since you can process the same key several times. Can you just add already seen keys to the key value store?
What keys? I'm sorry.
Already seen keys to the external key value store?
Which one
Already seen.
Oh, okay, already seen, yeah. So the question was if I can't just flag the keys that I've already seen. So like I said, there is a solution like that where as long as the partitions have not changed, you could use the Kafka offsets to say which offset I came from, like which offset this key actually descended from throughout the pipeline. But repartitioning by reducing or stuff like that could make this a little bit harder. You'd have to write like custom partitioners, and I don't know, I haven't tried that. So this entire experience got me to think about a model. And I wasn't actually trying to think up of something, but rather to look up something, because it's easier, and this is what we usually do. And a Spark job, a job is an overloaded term in Spark, so a Spark pipeline is a direct acyclic graph of operations. And it usually has sources and sinks, which are the roots and endpoints for this graph, right? And we saw that event time really matters. But it's not just about like putting the events in the right time window for the computation. You also have to reason about a lot of other things, like, okay, when did I see enough events to emit the output? What do I do with late data? And how do I re-output? I recompute and then output, and how I mean, how do I reason about that? How do I decide if I do the entire recomputation or just the delta or whatever? And when am I done with this computation and I just can discard it and that's it? And those are really bothering questions, at least for me. And I've stumbled upon a nice project. Cloudera Labs had a Spark Dataflow project. And they were actually doing something really interesting. They were using Google's SDK to write data processing pipelines over Google Cloud Compute, Google Cloud Platform. And they used it to write Spark batch jobs. And that was really cool for me. So I found myself trying to play with it around and do the same for streaming. And this is an ongoing effort for me. And if anyone wants to join, you're welcome. And so to conclude things, I would say that stateful processing is not straightforward. It has to be reasoned about. You have to think a lot about event time, because most analytical questions will talk about event time windows and sessions. You don't just count forever. You have to have like the context of time as well. And once you do that, you have to relate to late data, to reason about late data and out of order data, and about how you output and when you output, and it's all very bothering. And eventually, exactly one semantics across the pipeline is also not promised. It's great that Spark has exactly one semantics for the engine itself. It's a very good start. But having those integrations end-to-end is really challenging. It's not easy, and it's still not there. But it is possible in some cases, and it will be better in the future. Now, I'm going to go over a little bit about what Spark's version 2 is going to present, and the future of version 2. And I think this was influenced a lot from this model that Google contributed. And I actually know that it was influenced a lot. And I think that also other projects like Apache Flink have adopted this perception. They have adopted it completely. And basically what Apache Spark is going to do in version 2 is present something new called structured streaming. They are calling it doing stream processing without having to reason about it. If anyone's seen one of the slides or lectures they do in the last year, that's the slogan. What basically it means is that they are going to do event time windows starting from version 2.0, and the state is just going to be managed behind the scenes. They are going to present the idea of triggers, which are what to do with a new event that comes into the pipeline. Do I start to recompute now, or do I wait and do it in 10 minutes or whatever? And this is going to be available with 2 something down the road, probably 2.1 or later. Output modes as well. Is my recomputations going to be a complete output of this computation or just delta? And end-to-end sources and sinks are going to provide, hopefully, exactly one semantics. They're going to actually handle this end-to-end, finally. Version 2.0 is going to provide end-to-end handling of sources and sinks for files. And they said they are going to try and get Kafka source in and also SQL sync in as well. I don't know where this stands. And finally, state store API. Which means that any versioned key value store API could work with it, and Aerospike is any versioned key value store API, and that was why this choice was really good for us, even though we did not know so far ahead. And this also, I think, proves the fact that it was a good choice to decouple the state from the stream itself. And this is going to come out of the box with HDFS support. I've seen some slides about HBase, but I'm not sure. And I hope we could contribute the implementation for Aerospike. Yes?
By the way, a question about Aerospike. Is it only for keeping state or for serving data for later on processes?
So both.
Both.
Yeah. And this was also, we wanted to have the state available. So, yeah.
Is Spark 2.0 also in micro-batching or?
Okay. you remind me something. So the question was, is Spark 2.0 is going to be micro-batching? Basically, Spark 2.0 is not about these streams. It's actually working with Spark's SQL engine. And it's important to note for two things. First of all, the micro-batch is being decoupled from the API. It's still a micro-batch underneath, but you won't have the batch interval API anymore. I guess it would just do its best. I don't know. But another thing to note is that these stream development efforts have moved to structured streaming. So all their energies going to structured streaming, and I think it's worth knowing that. And they're also saying that the founder of Spark, Matej, has a team in MIT working on replacing the micro-batch engine with native engine. And decoupling the API allows them to do that when they will have that ready. Allows them to do that like underneath without you noticing it. So thank you very much. I hope I've raised some very good questions here, and I hope I gave you some answers. And next after me is Tyler from Google. But if you have any questions,